Okay, so if you remember last time we talked about logistic regression, and we also looked at the code for that. Today we will talk a little bit about some other terms and some other classification algorithms, but mostly we will be looking at variations of the logistic regression and how to use logistic regression if we have multiple classes. Okay, so far we have looked at binary classification, meaning that we had two classes. But what will happen if we have multiple classes? The problem will be a little bit different. Okay, and we will also talk today about cross validation, and we will talk about regularization as well. Okay, so did we talk about cross validation last time? I think we did, right? At the end of the lecture, I think we did talk about cross validation. I will try to mention it quickly, and if you remember it, we can go ahead and go for something new. Okay, so we had cross validation when we said that if we have a training set, if it's like that, okay, we might decide to take a part of that to be training, okay, and another part to be validation. And we have a separate, completely separate data set for testing our classifier. Okay. And then we said we can change the position of this validation set. So it could be at the end like that, it could be here, it could be there, and so on. So we changed the position of the validation set and we use the remaining parts of data for our training, such that if we continue doing this, if we are splitting our data into 5 folds, then we would have 5 accuracies, and then we can take the average of that. Okay. And there is also another method called leave one out, where we can just leave one sample out. So basically, instead of having a validation including like 20% of our data, we can just leave one sample out and leave it to test our classifier. And then after doing that, we take the rest of them for training and we leave the other sample and so on, such that we would have a number of, let's say, folds, or a number of times we are testing this that will be equal to the number of training samples. Okay. Okay, cool. So what will happen if we have a problem with our classifier that is called overfitting? If you remember last time, we said that overfitting is when we have a model that is very tailored to a specific data. So if we have a training data looking like that, we might have a classifier that is very strictly tailored to this kind of data. Okay, and it's very complex like that. And we might have a classifier that is something in the middle. So given the same data, we might have a classifier that looks like that. Okay. Okay, so do you have a sound near you? Could you mute that sound because I'm hearing it?
I have to do that.
Okay, so if we looked at another one, another classifier, you would see that this classifier could completely be underfitting our data, meaning that it is not really learning something meaningful. So here we have a classifier that is overfitting our data, and here we have a classifier that is underfitting our data. Okay, and what we have here in the middle is a compromise between the two. Okay, so what is regularization then? Regularization is basically us trying to take a classifier that is overfitting our data to be more like the classifier in the middle. So instead of having a classifier that is very strictly tailored to this particular data set, such that it's almost memorizing the sample points, we need the classifier to be a little bit generalizable. Because again, remember, we will have an unseen data, unseen sample looking like that. If the classifier is very strict like that, if it's overfitting the data, it might miss something that is unseen because it's just memorizing the training data. Okay. If it's underfitting the data, that's a bad classifier because it's not learning anything good. So we need this classifier in the middle. Okay. So regularization is basically taking a classifier that is having overfitting with our training data and going to the direction of underfitting basically. So it's making it a little bit easier, a little bit less complicated, and it doesn't memorize the data. So there are some approaches to doing that. Some of them are like collecting more data. So we can collect more data. And the good thing about collecting more data, you will have a lot of data points. So the classifier would have a chance to train itself on more data points. And this would make the classifier not overfit with our data, but it will just be learning the new samples, and then it will be able to see the unseen samples. So collecting more data will add more variations to the classifier to train on, and this will make the classifier better with unseen data. Okay. The other approach is to introduce a new parameter to our cost function. This new parameter is called the regularization parameter. Okay, and it has this simple lambda. Okay, and we can go ahead and plug in this lambda value to do the effect of this regularization. Okay, so we have two approaches. One of them, two methods. One of them is called L1 regularization. Okay, and this is also called lasso regularization. And the other one is called L2 regularization or reg. Okay. So let's see the equations and let's look at the differences between them. So first of all, let's get our cost function. That's our cost. And we will be using the sum squared error. So the sum squared error was basically like that. So we go on all of our samples sy of I, and we square this. Okay, so the addition that we would have on our cost function would be to add this lambda term. So let's write it in a different colors so that we see that this is u to the cost function. So that's lambda. Okay, and this is multiplied by the absolute value of the weights. Okay, and how do we get this? We basically sum over the weights. So J is an iterator that goes on all of our features. Because remember, every feature is associated with a weight. So that's why we're going on the number of features. Okay. And then we're just we're just adding them together. Okay. So basically, we take the value of every weight and we take the absolute value of that, and then we add them together. Okay. And then we multiply by this lambda value. Okay. Okay, so how about the L2 regularization? The L2 regularization is basically using the same Gusta function, and then it will be a little bit different in this part. So it will look like this. And then here we have W squared. Okay. And the way we get this is simply by, again, adding the values of feature weights. Okay. But this time we are squaring the values. So you go over all the weights and then you square each one of them and then you add them together. Okay. And by the way, mathematically, this is equivalent of taking the weight dot product itself. So you can say that this is W transpose multiplied by W. Because when you are doing dot product, you're just multiplying this with the corresponding element and so on. And then you are adding them together to get one scalar value. So you can loop on them, or you can do it like a dot product. I would prefer doing this like a dot product because computationally that would be quicker in Python and in MATLAB. Okay. Okay, that's good. So right now we would have our two methods. We just have a variation of our Gusta function. Okay, so what is really the effect or the added value of the lambda parameter that would achieve such effective regularization? Okay, so the effect of lambda is something that we call weight decay. Okay, or we call it weight shrinkage. Okay, so you would see the two terms being used to describe what is happening here. Okay, and let's just think about it. It's very intuitive because thinking about this part, okay, and what is really happening if we make this part higher in value. Okay, let's think about it. We have the ghost. We have our Gusta function, and our objective is to pick up the weight values that will make this ghost as small as possible, right? So we are trying to find the weight values because, of course, that's the transpose X if we are using something like other line. Okay. So we are trying to get the weight values, okay, and bias that will minimize this cost. Okay. So now let's think about this term. So we are adding this to the cost. We're adding this to the cost. So anything positive in this part is actually increasing the cost. It's making the cost higher. Okay. Okay. So, and that's exactly what we are doing here. So we are plugging in the lambda value such that when we increase the value of lambda, when we have higher value for the regularization parameter, it has to minimize the value of the weights. It has to shrink the value of the weights such that this term is minimum, such that this term is very low. Okay, because remember, we need to make this minimum. So we need to make this term as close to zero as possible, right? We need to have a very low value for this. So that's why when we increase the value of lambda, this would decrease the value of the weight to make this term small. Okay. Is this clear?
Yeah.
Okay, that's good. And that's exactly what we are trying to do to achieve the effect of the weight shrinkage. So if we imagine that we have several weights, and this is, by the way, a very famous plot that we can have from our data, just see what is happening for every feature. So we can imagine that we can look at the value of lambda across time and see what is happening when we increase the value of lambda. So let me plot this figure that should visualize the effect of lambda when we increase the value of lambda. So we are putting lambda on the x-axis, okay? So we're starting from 0 and we're increasing the value of lambda. When we increase the value of lambda and we observe what happens to the value of every weight, this is exactly what happens. The value of the weight will get smaller and smaller when we increase the value of lambda. So it will shrink, it will go close to 0, whether the value is negative or positive. Because remember, we are taking the absolute value or we are squaring, okay? So the direction doesn't matter. What matters is this value of the weight has to shrink. So it has to go close to 0. Okay, so this is, let's say, the value from W1 of the first feature. Let's say we have another feature looking like that. So each one of them will decay differently according to the values of the features. Okay, and perhaps we had like 4 features in our data. Okay, so do you have any questions on that?
No.
Okay, perfect. So this is really achieving the effect of weight decay. Okay, when we increase the value of lambda, the weights will just decay like that. And when we have our weights decaying like this would make the classifier go to this direction because the weights are being smaller and smaller. Okay, and this effect in L1 regularization could actually make the weights go to 0. And when some weights go to 0, this would mean that we are rejecting some features because the weight is multiplied by the value of every feature. So if the weight is 0, this would mean that we are not taking into account the value of this feature. So this is precisely achieving the effect of making the classifier generalizable or making it easier because it's now neglecting some features, almost selecting the features, okay? And L2 regularization will also shrink the weights, but it wouldn't be almost 0. So let's see why this is the case. So let's remember the relationship between the weight and cost that we had, okay? And let's say that this is W1. And let's say instead of having this as 1D, I would like to put it as 2D directly. So this is between W1, W2, and it will be actually 3D because we would have the cost, as well. So we have the minimum cost here, and then we have different values. And then would like to start from a point, a random point, and then navigate this until we reach this global minimum.
Yeah.
Okay. So if we imagine that now we are not just trying to come up with this part. So we are not just trying to come up with the weights that would optimize this part and just minimize the cost. We now need the weights that will perform this and also perform this part. So we need the value of the weights that will be decaying. They will be minimum, okay, to achieve minimum cost. So the weights got to solve the two problems at the same time. Okay, so let's look at L1 regularization. So we just said that we are gonna add these together. So basically we are adding the values of the weights. So it will be W1 plus W2. It will be like this. So if we looked at this relationship of W1 and W2 and just taking the absolute value of each one of them, like so, and we plot this, it will look like a diamond. Okay. It will look like this. Okay, that's now a part of the solution that we are trying to get. Okay, let's remember something. Let's remember if we have a line, okay, and we need to solve with this equation with another equation that is describing a different line. So we need really to get an x value that would satisfy both of these equations. Then we would be thinking about getting the x value of the intersection of them. Right? Is this clear?
Yeah.
Yeah, because the x value is satisfying both equations, so it has to be the point of intersection. Okay? I am using this analogy here. How? Because my weights should be satisfying both of them. It's satisfying the relationship between the absolute value of W1 and W2, and it's in the meantime trying to go in the direction of the global minima. So it should be satisfying this ellipse right here. So basically, I'm looking at almost at the intersection between the two. And if we imagine that we are starting from the global minima and we are making this, so let's imagine this part. So if we imagine that we are starting from the global minima and we are trying to make this bigger and bigger and bigger and see the relationship like that, then we have a high probability of intersecting with the absolute value at this point. Okay? We have a high probability of intersecting with this point. Okay, so what is the meaning of this point? This point means that we have this value for W2, okay? But the value of W1, which is the solution, by the way, so that's the solution, that's the value of W1 and W2 satisfying the solution that we want, okay? So it's almost like the part of the global minima intersecting with this, okay? So it will be 0 for W1, right? Because that is the solution, it will be 0 for W1, okay? So 0 for W1. So what happened here is that we call this solution a sparse solution. Sparse solution by mathematical definition means that if we have many solutions to our problem, then the majority of our solutions are zeros. So we have very few solutions that are non-zeros. Okay, that's the meaning of a sparse solution. And that's exactly what is happening here, because you would have many of your weights to be zeros and few of them will be of a positive or negative value. Okay. Is this part clear of L1 regularization?
That's for L1.
Okay. So what will happen for the other solution?
This for L1.
That's for L1.
Oh.
Okay, so by taking the absolute value, that's why it was looking like this. Okay, but looking at the square value, it's different. We would look at the square value because the square value would mean that you are taking the first one plus the second one. Okay, the square of the second one. And by the way, if you look this up, this is like drawing a circle. Taking the x squared plus y squared, that's like drawing a circle. That's the equation of a circle around the origin. Okay, so now the relationship between our weights, W1 and W2, will be circles. So it will be like that. In the meantime, we have a solution that we need to optimize. So we are trying to optimize this. We are trying to look at when this global minima will hit our curve, because the point of intersection is again the solution. And if we do this multiple times with different problems, you would see that it's very hard to get a value of 0. Okay, that's why this L2 regularization is not giving a sparse solution. Okay, so when you look at the solution of that, you would see that we have a projection here. So that's W1 of the solution, and that's W2 of the solution, and the same thing goes here. Okay, that's why L1 regularization would achieve this behavior of selecting some features or removing some features, making the weight value of 0. And in the meantime, L2 regularization would shrink the weights but not make them go to 0. Okay.
Yeah.
Okay. So do you have any questions on this part?
No.
Okay. Okay, good. So let's save this.